All right, guys, so we're going to be looking at number 38 from your homework set. Oh, that's wrong. We're going to be looking at number 4. And it's kind of a long problem, so I have a PowerPoint. So let's go over to the PowerPoint and see what we have. Okay, so we have that a bacteria culture grows with a constant relative growth rate. That's a key word for exponential function, okay, exponential growth. The bacteria count was 400 after 2 hours and 25,600 after 6 hours. So they want to know what is the relative growth rate. So that's K. So we have to find K. And then part B, what was the initial size of the culture? So we have to find C. Okay, and then once we know K and once we know C, we can find an expression for the number of bacteria after T hours. All right, so let's get started. So what we know is that after 2 hours, so first of all, we know it's a relative growth rate, so we're going to be using this function, or we can also use something like this. Okay, so and why is the population? Why is how many bacteria? And we're given some information. After 2 hours, there's 400 bacteria. And then after 6 hours, whoops, sorry about that. After 6 hours, there's 25,600 bacteria. And so our job, sorry, there's a hair on my screen, is to find K, the relative growth rate. And then after we find K, we're going to find C, the initial population. Okay, so this is really a systems of equations, right? We have 2 equations and we have 2 unknowns. So we're really gonna, again, we're gonna handle this like a systems of equations. So let's write this out. We know this is gonna be modeled. This is gonna be the structure of the model because it's an exponential function, exponential growth. And so let's plug in time t equals 2 to our equation like that. And we know this equals 400. And then we're going to plug in 6 and we know it's going to equal this. Okay, so there's lots of ways that we could solve this. For those 2 unknowns, how I like to approach it, doing ratios. So I start, for instance, with the higher power, which is 6, right? 6 is bigger than 2. And I create a ratio. So I'm dividing the top equation by the bottom equation. All right, and since we have these equal signs, this is going to be the same as dividing 25,600 by 400, right? So the bottom divided by this, bottom divided by this. And since everything's equal, we know that these proportions have to be equal. All right, and why I like to do that is we get a lot of nice canceling. For instance, we're going to be able to cancel, that's C. That's the initial population. That's what we're going to find in part B. And then we can use our exponent rules here, same base division, so we can subtract 6K minus 2K is 4K. So 4K is going to be equal to this expression. All right, and then that's not so bad. We know how to solve this. We solve exponential equations when the variable's in the exponent. We solve that using logarithms. So we take, I'll do the natural log since the base is e. I'll match the base. Take the natural log of both sides. And I do that because that brings the variable down in front. And natural log of e is just 1. So that is going to go away. All right. And then, like I said, we can clean some things up. That's going to go to 1. If you do that in your calculator, that's just going to be 64. Isn't that nice? Okay, so then K, we're almost done. Divide both sides by 4. I like to think of that as just multiplying by a 4th. And then we get that. Okay, and then that's fine for K. If you wanted to put it into your calculator, this is the exact value of K. The approximate value, we use swivel because we have to round. We can throw that in our calculator. And we should get something like this. Okay, and then there you go. Okay, so that's our K. Let's go back up here. So now in our formula, we know K. So the only thing we have to figure out is the C. So let's go ahead and do that. That's part B, the initial population of the bacteria. All right, so C equals question mark. So all we have to do at this point is to choose one of the equations, right? For instance, we could use this top one. This is exactly how we solve systems of equations first, right? We use the 2 equations to figure out one variable, and then we plug the variable back into one equation and solve for the other variable. Same strategy, whether it's a linear systems of equations, quadratic systems of equations, or now in this case, an exponential. So let's bring this expression down to part B. All right, but we just figured out what K was. So let's make that substitution. K was 1/4 the natural log of 64. And we know that's 400. Okay. So let's see. What's 2 times a fourth? That's a half, right? And then we also know when we multiply a logarithm by a number, we can bring that number into the argument as an exponent. So I'm going to do that. So natural log of 64 to the 1/2. What's 64 to the 1/2? It's like the square root of 64. What's the square root of 64? Yeah, it's 8. Okay. So, so far so good. And now let's see. So E natural log of 8. Well, this is our composition of inverse functions, right? The E and the natural log essentially cancel. And so now it's just C times 8 equals 400. So all we have to do to get our initial population, let's divide both sides by 8. Our initial population is 50 bacteria. 50 bacteria. Okay, so we have K and we have C. So now in part C, we're going to put all of these pieces together and we're going to get a model for the population. Y is the population of bacteria as a function of time. Okay, so Y of T is equal to C, the initial population, which is 50, and K was 1/4 natural log of 64, and then times T. Okay, and I'm going to clean up this expression. Let's move T, just rearrange it because it's products and factors, and that's what we can do with products and factors. So this is really going to be 50 e to the T over 4 times the natural log of 64. And just like we did in the previous problem, numbers in front of logarithms, we can move them into the argument as an exponent. So let's do that. So we're looking at 50 times e natural log of 64 t to the 4th. All right, and then look at this. E and natural log are going to cancel for reasons we've said lots of times before. So 50 times 64 t to the fourth. All right, and then there's our exponential function. So lovely, right? I'll put that little box. That's part C. Okay, so now we have this model that's going to be exponential model that will model the growth of our bacteria. Okay, so where are we at? So part D now. So they want to know, find the number of cells after 4.5 hours. Okay, and then we'll see what that looks like. Okay, so part D. We want to know the number of cells or bacteria after 4.5 hours. Okay, so this is still algebra, right? We haven't used a lot of calculus. This has all been algebra so far, right? Okay, so all we have to do here, if time is 4.5 hours, and we want to figure out the population after 4.5 hours, we're just going to plug it in at t. Okay, so throw that in your calculator. Okay, to get your amount of cells, amount of bacteria. And I would accept that as an answer. But if we're in between cells, that means we're almost going to make another cell, but not quite. So I'm going to assume we have to have integers for cells. So I'm going to say we're still at 5,381. Okay? All right. But I would accept either answer. And now we want to know, find the rate of growth after 4.5 hours. Ooh, a nice key word there. Rate of growth. It's like rate of change. What are we thinking of? The derivative. So they want to find the derivative. They want us to find the derivative at t equals 4.5. Okay, so here's our y function. And now we want to find the rate of growth. Okay, so we have to find the derivative of y. And let's see, this is an exponential function, and we're going to have to use the chain rule. Constant, we can just kind of ignore till the end. So the derivative of an exponential function, normally it's e to the x, but if our base is different, it's b to the x times the natural log of b. So that's the derivative of the outside function. Oops, except our base is 64. And then the derivative of the inside function, this is really 1/4 times t, so it's just going to be 1/4. Okay. And we know we can fool around. We can move that fourth, put it in front. And that's pretty much the only cleanup we can do. That's worth doing. Okay. And so now what the question is asking, they want us to find the growth rate at 4.5 hours. So let's plug in 4.5 hours. Okay, that's the exponent. And then we're going to multiply by the natural log of 64. Okay, so what are we going to get? So throw that in your calculator, and you guys should be getting something like 5,595. Okay, and remember this is y prime is dy dt. And y is telling us the number of cells, and time is in terms of hours. So this is saying the growth rate is 5,595 cells each hour. Okay, and that's only at that time rate, right? As time is increasing and our growth is exponentially growing, the growth rate is also going to change, right? Changes each moment. Okay, good. Final question, right? And again, we're going back to algebra. We want to know, when will the population reach 50,000? So now we're back at algebra. Okay, so part F. We want to know when y of t is equal to 50,000, right? When does that happen? Well, let's bring in our y function, which is 50 times 64 t over 4. Right? Where are we going? I forgot our function. There it is, 50 times 64 t over 4. Okay, we want to know when that's equal to 50,000. Okay, and we have to solve for t to the 4th. So this is an exponential equation. So how we solve it is we isolate the exponential expression. And when our variable is in the exponent, to get it down from the exponent, we take the natural log of both sides. So let's take the natural log of both sides, and that allows us to bring the exponent down in front. So t over 4 times natural log of 64 equals to natural log of 1,000. And we solve from there. So let's divide both sides by natural log of 64. And then we're going to have to multiply both sides by 4. So I'll do it step by step. Okay, now we multiply. And then this is ready to get thrown into our calculator. And we get that the time is going to be about 6.6. And again, what are the units on that time? It's going to be hours. All right. So there you go. So that's how we find that's how we do our exponential problem. And again, a lot of this is algebra. A lot of it's algebra. The parts that are not algebra, just kind of scrolling back up, is how we derive this function. And again, how we derive that function, that's calculus based, because we figured out that the derivative has to be proportional to the original population. And only exponential functions satisfy that. Okay, so that's the calculus part. The other calculus part is when we're talking about growth rates. Okay, so that's why we're looking at this again in calculus. Also, it's a tricky subject, right? So it's nice to have a little bit of a review. Okay, so that's the exponential growth. Let's look and see what happens when we have exponential decay. Okay, so exponential decay, like I said, it's normally like radioactive substances, unstable substances that break down, right? Also, like when you have a cup of coffee, you have a lot of caffeine in your body at first, and then how that caffeine leaves your body is also by exponential decay. It has a half-life. So here we go. So let's look at an example of that. So here we have that this substance has a half-life of 28 days. That means after 28 days, half of it will be gone. All right. And then another 28 days passes, and then half of it will be gone. And then another half, and another half, and another half, and another half. And it never technically actually reaches 0, but it gets pretty darn close, right? So here we have that a sample has a mass of 50 milligrams initially. Find a formula for the mass remaining after t days. Okay, so first of all, when we're talking about half-life, that's exponential decay. So what number is this? It's number 8. So we're talking exponential decay in this example. So we're still going to be using our same model. Okay, they also tell us, what else do they tell us? That there's 15 milligrams initially. Okay, so they're also telling us initially we have 50 milligrams. So we have this going on. So if we wanted to model how many milligrams of this substance is left after T hours, we're going to have to figure out our K. And we have one more piece of information that's going to help us with that. We know that the half-life is 28 days. We know that the half-life is 28 days. So let's go back and think about our problem. And after 28 days, so T is equal to 28, we plug in 28 for T. If we start with 50 milligrams, after 28 days, half is going to be left. So how many milligrams are we going to have? Half of 50. We're going to have 25 milligrams. So using that fact, now we have one equation and one unknown. So we can go ahead and solve this for K. So isolate your exponential expression. So divide both sides by 50. And it should equal half, right? Because we're dealing with a half-life right now. What do we do when our variable is in the exponent? We take the logarithm and bring it down. All right, so that's your strategy for variables in the exponent. What's the natural log of E? Just 1. And so we're almost done finding our K. All we have to do is divide both sides by 28. And again, I like to think of that as just multiplying by the reciprocal. Whoops, I wrote that weird. Let me write that again. That way, when we write it in our equation, we can bring this 1 over 28 into the exponent. Okay, so where are we at? So we know then that y of t is going to be equal to the initial population, or the initial mass, times e to the k times t, and k is this. Okay, so just like before, I'm going to take this t and move it to the front. And now this whole number multiplied by a natural logarithm, I'm going to move it into the argument as an exponent. And that's going to be our model. Well, almost actually. We have one more step. Oh. All right, so t over 28. And the last step, e and natural log essentially will cancel, but it's a composition of inverse functions. And we're left with 1/2 times t over 28. Okay, and let me just make a quick observation here. So this is your answer for part A. And remember, we're dealing with exponential decay. And notice that our base is 1/2. When your base is 1/2, that's when you're getting your exponential decay graph, right? When your base is between 0 and 1, your exponential function looks like this. All right, so it's a good thing our base is 1/2. Okay. What else is happening here? We want to now find the mass remaining after 40 days. Okay, so let's see. After 40 days, I always like to think of the half-life. Half will be left after 28 days. If you double the half-life, right, so another 28 days goes by, so it's 56. Now that you're going to take half of the half. So after 56 days, you'll have a quarter left. Half of half is a quarter. Okay, so we're falling somewhere between that. So 40 days, we should be having half to a fourth of the original mass. Okay, so part B, what happens after 40 days? Time t equals 40. Well, we just had a formula for y. That was the hardest part, and now we just get to plug in things. And it's going to be t over 28, but now time is 40. Okay, so this is saying, how many multiples of the half-life are we going to have? And if we throw that expression into our calculator, we should be getting something like this. And then what are the units going to be? What does y mean in this case? It's how much mass is left. So this is going to be milligrams in terms of milligrams. All right, so where are we at? Part C. How long does it take the sample to decay to a mass of 2 milligrams? That's crazy. All right, so here we are at 50. And I always like to kind of think, so going from 50 to 2, I'm just going to do kind of a guesstimate to see how many half-lives we're going to have. So the first half-life would take us to 25. And then the next half-life would take us to 12.5. And then the next half-life would take us to 6.25. And the next one would take us to, what's half of 6.25? So do you see what I'm doing? Divided by 2, divide by 2, divide by 2, divide by 2. Okay, so we're getting closer to 2. And then if we divide that in half, it's going to be 1.5 something. I'm just going to write 1.5-ish. Right, we could really get technical. Or exact, rather, not technical, but we can really get exact. There's the 1.5-ish. 1.5625, okay? And we want to know how long it has to take to get to 2 milligrams. All right, well, this is, the first half-life is 28 days. And then the second one is, what's 28 times 2? 56 days to get here. And then we have to do another half-life, and another half-life, and another half-life. Okay, so it ends up being, I'll just kind of jump to it. 2 is between here, right? 2 milligrams is between the 1, 2, 3, 4, 5, between the 4th and the 5th cycle. So it's going to end up being 4 half-lives is 112, 5 half-lives is 140. Whew. And this is all kind of a thought bubble. All right, this is us guesstimating what's going to happen with our formula. Because that's how the half-life works, right? We start with 50, we take half of that, it's 28 days. Another 28 days gets us another half. Another 28 days, we go down by half again. Another 28 days, we go down by half. Another 28 days, we go down by half. And that ends up being 4 to 5 half-lives, which is equivalent to 112 to 140 days. Okay? So let's see what our formula gives us. All right, so if we wanted to, of course we could have skipped here right off the bat, but what's the fun in that? We want to know, let me start over. We want to know when y of t is equal to 2 milligrams. Okay, so we have 50 times 1/2 t divided by 28 is equal to 2. And now this is just another exponential equation to solve. So we isolate the exponential. So divide both sides by 50. 2 over 50 is like 1 over 25. Let's take the natural log of both sides, since that variable is in the exponent. And now our logarithm rules tell us that we can move the exponent out of the argument down in front. And now we're ready to solve for t. Divide both sides by the natural log of 1/2. solving for t. Final step, well, penultimate, we still have to put it in our calculator, but multiply both sides by 28. And you have a nice little equation you can put into, or expression rather, you can put into your calculator. And what should you get? You should get about 130 days. And what do we guess? It is 130 days between 4 to 5 half-lives. It is, right? There's our 2 milligrams. Here's 4 half-lives. Here's 5 half-lives, right? 112 to 140 days. We said 130 days. So there you go. So that looks pretty reasonable. Okay, so let's pause here. In part 3, we're going to talk about Newton's law of cooling, and we're going to look at an example of that as well.